So let's get started. And the first presentation this afternoon is from Nick Brummell about the sun. How about that? The sun.
The sun, yes. Hello, everybody. Yeah, my name is Nick Brummell, and I'm going to be talking about some work I've done here with a series of graduate students over the years, starting with Kelly Klein way back when, then involving Jeff Vassell, who some of you know. Uli just mentioning him. He's now at Edinburgh, so he's much nearer than he used to be. He used to be in Australia. Christina was a summer student that worked with myself and this other graduate student, Bishek, last year. But Bishek was also another graduate student, just recently graduated now and working in Boulder. So a long series of work with very productive, awesome graduate students. So obviously, I did very little, and these guys did all the good stuff. I work on lots of things to do with dynamos. I work with Steve and Faust on essentially nonlinear dynamos. I've worked for many years on sort of compressible convection in its various forms for doing various things, including being a small-scale dynamo. Right now, another graduate student working on the lunar dynamo. I've worked on theories of the solar tachocline. I've worked on magnetic buoyancy. And this time, I'm not going to, all of these things which explicitly mention dynamos, I'm not going to talk about, which may have been an unwise decision in choice of talks for a dynamo conference. But I decided to talk about magnetic buoyancy things and flux tubes. So you may ask why. Well, the workshop description said various things like this. I was interested in the latest state of observational evidence for spatial structure, talked about things like constraints for dynamo theories posed by magnetic observations, and said things about differences between dynamos and planets and stars. So I took this to heart, which means I didn't actually have to talk about specifically dynamos, but this sort of stuff. And so the why is this, why are magnetically buoyant flux tubes interesting in this context? Well, potentially controversially, I'm going to make these statements. Flux tubes are the germination point for all of our current understanding of all dynamos. This was essentially the thing that started dynamo, or kicked dynamo theory off in many respects, started the whole ball rolling. And they're talked about endlessly in the solar context, but hardly at all in the planetary context. And that may be just because we can see the surface, the upper reaches of dynamo things in the sun, but we can't see the upper reaches of dynamo things in planets quite so easily. So there may be a good reason for that, but it's interesting that flux tubes are talked about endlessly in the solar context, but not in other contexts. And here, even though flux tubes led to these ideas, which we now incorporate in our dynamo models, there are no full dynamo simulations of large-scale dynamo fields that connect to things like flux tubes directly. We do not see flux tube scale emergences from our larger scale dynamo models. So that's a problem, because they are the things that motivated, those are observations that drove us. And so we haven't completed that circle where our theory has come back to explain where these things come from. So I know these are somewhat provocative, and some people might argue about these things, but I think this gives me an excuse to talk about what I'm going to talk about. So to explain some of those things a little bit, you've all seen these things before, and you're all very familiar with this, of course. The solar observations of the surface of the sun, we see sunspots, we see active regions, we see clusters of these things, and they have very particular characteristics, which immediately suggested to people that when we knew these things were magnetic, that these are the manifestation of sort of tubey-like things poking through the surface, right? This explains Hell's polarity law, because then you get a sign of stuff coming out and stuff going in, and they're slightly tilted, which is Joy's law, which sort of suggests, okay, if you get a loopy type thing and there's some rotation acting on it, maybe that can tilt a little bit. And these are where our formative ideas for dynamo theory came from. And Gene Parker was responsible for a lot of these. And then they got sort of more codified into mathematics through mean field theory with Stringbeck, Krauser, and Radler, and everything like Keith described on our first day on Monday. But this order gave us all these ideas. The butterfly diagram suggested this thing had to be a dynamo, can't be a fossil field. Hell's polarity law said, oh, it's coming in and going out, coming out and going in. That has to be a toroidal field. Joy's law tilt says, oh, that's sort of suggested that rotation or symmetry breaking may be something that gives you toroidal conversion to poloidal field. And then off we went into codifying these as alpha effects, et cetera, right? But this was the initiation of our intuition regarding the solar dynamo. So this sort of little flux tube cartoony stuff, thanks largely to Gene Parker, was what sort of kickstarted all of these ideas in many ways. And the surprising degree of order that you get out of this chaotic turbulent system makes you realize that there's much more to it than just these little cartoony ideas, but that's where it came from. But these rules are great constraints on our understanding, and we have to figure out how our theory sort of obeys these rules if we want to understand things. Now, so these were observations which became constraints, led to our initial understanding. There are some newer observations, or more recent observations, which I think are very interesting and provide new and different constraints. So magnetic helicity, most of you know what this is. It's a volume integral of A dot B, where B is the curl of A. It's the potential for the magnetic field. But as described by great early work by Keith, and then following work by Mitch Berger and in great gory detail, you can think of this as a way of measuring the twist, writhe, and linkage of magnetic fields, right? And this is key in dynamo theory, because if this is ideal MHD, then this is a conserved quantity, so that's a really strong constraint, and that's where you realize that linkage can be difficult, because if it has to be conserved and things are linked and they amplify, that's not conserving helicity. You have to unlink things somehow, so that tells you that diffusion is absolutely necessary for a dynamo, etc. So this is an important quantity. So plays a major role in fast dynamo theory, but also the untwisting of things, or the release of energy from twisted things, is what we think drives a lot of action in the solar atmosphere, right? When initiates flare. I mean, we're not absolutely sure how all this works, but it can be associated with the initiation of flares and CMEs and all this sort of stuff. Obviously, there's all kinds of problems with this. If I'm taking curls of A's, there's a gauge to be dealt with, so that's a bit of an issue. So I mean, if we actually want to do observations, how do we measure A? That's a problem. So what a lot of observers do is actually measure the current helicity, which is the same thing except sort of curled one more time. It's the curl of B dot B itself, so J dot B, current dot the magnetic field. And this is eminently more observable, right? Because you can see line of sight magnetic fields, you can see gradients and horizontal magnetic fields, and this is observable. So from observing helicity, and there's all kinds of weird things to do to actually do this observation. You may have to assume force free, and then use an alpha. This idea, it's a different alpha, not the alpha effect alpha, but there's another measure called the alpha coefficient, which is essentially J divided by B. And obviously you're not doing a nice closed volume integral when you're doing a patch on the sun. So there's all kinds of issues to do with this, but you can measure elements of and aspects of helicity. And if you do that over a solar cycle for a bunch of active regions, you get this cool little plot right here, which is over a solar cycle, and it's a plot of measured helicity by some means in active regions over that cycle. And here, a dark circle indicates that positive helicity is detected, and an open circle or a white circle is negative helicity. And this thing called the solar hemispherical helicity rule emerges from this, and you can see it right here. The majority of things in the northern hemisphere here are white circles with a few black circles, and in the bottom, in the southern hemisphere, the majority of things are black circles with a few white circles. So this is a rule. It's a weak rule in the sense that not everything is a white circle at the top. There are a few black circles. There are a few violations to the rule. And in the southern hemisphere, everything is mostly black circle with a few violations of that. So the rule says that generally negative helicity in the northern hemisphere, positive helicity in the southern hemisphere. And if I showed you the next cycle, it would be the same. It does not reverse in cycle. This is the true over all cycles. So this is known as the solar hemispherical helicity rule. And it's another constraint, right, that we have to satisfy and wonder where this comes from. Yeah, that stuff I already said. Okay, so active regions poking through the surface are, we believe this in that cartoon-like picture, things poking through the surface, these little tube-like cylindrical things poking through the surface. How do they get there? Where do they come from? Well, come from the deeper interior. We're not actually sure exactly where, how deep in the interior, but let's address that in a second. But how do they get there? They rise by magnetic buoyancy. And I think most of you know this. If you have a concentration of magnetic field, that contributes the magnetic pressure to the total pressure. If you think the total pressure equilibrates quickly, that reduces the gas pressure, that reduces the density. If temperature equilibrates quickly too, or quicker than other things too, then that an element, a concentration is buoyant. So that's magnetic buoyancy, also a Gene Parker idea, right? Like I said, how deep do they come from? We're not absolutely sure. Recent simulations have big bands, wreaths, often people would refer them to, of toroidal field appearing in the base of the convection zone. So maybe that's where they appear from. The old idea was that it was mainly in the tachycline was likely to be the origin because of a great deal of shear. That's a great place for amplifying magnetic fields. I'm sure you're familiar with. Other ideas, maybe it all just comes from the near surface. Maybe there's some mechanism which sort of agglomerates magnetic field near the surface. There's also a lot of shear there, and maybe that's. But we don't really know. But I'm going to work on this principle. That's the old one, that it came from the tachycline, and we can talk about that or dispute that and discuss that as much as we want, but let's work on that principle. Then there was a lot of modeling built on this intuition. We say, okay, we want to model flux tube cylindrical-like bundles of magnetic field arising from the deep interior, possibly the tachycline, possibly generated by shear. Let's start it and let's do it. And there's lots of ways of doing that. We started off with simple things, but Hengsfried and Defoe, thin flux tube approximation. This just means that I'm not modeling a finite width flux tube. I'm just considering the properties, the magnetic properties along a line. So in other words, a one-dimensional affair. And we got a tremendous amount of intuition from that early work. You, of course, want to generalize this to sort of something which has a finite cross-section, where you can do tension forces within the tube and twist within the tube more accurately. And there was a whole industry of people doing these sort of stuff between when it started and now. So it's been going for a long time. And like I said, we learned lots of things from these simple approaches early on. We learned that twist is essential for the coherent rise of a flux structure. If it's untwisted, then it just rises a little bit, and then the vortex wake that drives it up after the magnetic buoyancy initiates it rips it apart. So you need twist. So immediately you know that you're expecting anything which emerges to have some helical content because it needs twist to be coherent. And we got all kinds of estimates for what flux strength should be at in order to have emergence at the right latitude from thin flux models and this sort of stuff. So a lot of our intuition in Dynamos about the expected field strength at the base of the convection zone and stuff like that comes from some of these very, very simple models. And these are vastly simplified. So people have sort of taken as read for a long time now some of the values that came out of these calculations, but we should approach them with a bit of caution because they're very simple models. Okay. So that was one way of doing things, was by do little models of little cylindrical flux bundles, isolated bundles in a quiescent field-free background. The other way to do things was to actually, those are not instability calculations, the previous ones. If you put a flux tube in there, it's necessarily less dense than the surroundings and it rises. It's not an instability calculation. You can actually do magnetic buoyancy as an actual instability calculation, and the linear instability and everything has been calculated by Atchison and various other people in various different forms over the years. But these are simulations by my good friends Fausto Catania, David Hughes, Paul Matthews, Mike Proctor, many of whom are in the audience today, where you essentially just put in a layer of magnetic field, which decreases where the field increases sufficiently with depth. So the magnetic field in some sense is getting more and more evacuating of the density as it goes down. And then even if the stratification is stable, it can overturn that stratification. So there's an instability, and you can follow the nonlinear evolution of this instability. Early work was done in 2 dimensions, later work in 3 dimensions. The cool thing is that you automatically, by this instability, get things which look flux tube-like, right? You get little, well, in 2 dimensions, little, it's independent of the 3rd dimension here. So it looks like a tube, but little mushroomy shaped tubes. And if you do it in 3 dimensions, you see these little mushroomy tubes. And you know, there are undular instabilities here, so they tend to give this arching, rising sort of flux tube type of behavior, which is exactly what you want if you want things to rise, arch, and poke through the surface of the sun and look like an active region. So very promising. Just want to show you another calculation that I did with Jeff Vassell. This is when we got involved in some of this stuff. In these previous ones, the layer was just inserted with in whatever form we want to insert the layer. All we did in this one was said, let's form the layer by having velocity shear act on a vertical field. So I have a vertically dependent shear acting on a vertical field. Then I get a horizontal field. It can go unstable to whatever it wants. No, it's stratified. These are stably stratified. Stably stratified. Yeah. So in that calculation, and this is possibly the most complicated, well, one of the more complicated simulations of magnetic buoyancy that have been done, in the sense that the layer is shear generated and it does the buoyancy thing however it feels like with all the shear present. But once again, you can see you get rising, arching, flux-like structures and these things, right? This is a very long movie. It's kind of cute. I won't make you watch it all, but well, can I even move it on? Yes, I can. So one of the things about this that I want you to notice, or 2 things I want you to notice about this. First of all, if you examine the twist in the calculation like this, the twist is all over the place, right? The twist is kind of random. There is no real mechanism that says the twist has to have any particular handedness. So maybe in realistic situations when tubes are formed, they are formed with a sort of random twist. This is going to be one of my suppositions throughout this. And the other thing is, if you look at this thing had a vertical magnetic field which got dragged out into a horizontal magnetic field. That horizontal magnetic field went buoyantly unstable. If you look at the field lines in such a calculation, they're all over the place, right? They are not confined to they're not field lines just confined to the structures. There are field lines which wind tightly in the structures or whatever, but also meet the exterior fluid. So the magnetic field in this case is volume filling, and we have a concentration of magnetic field somewhere in that volume filling field, which is very, very different from an isolated structure where I just have a magnetic structure in a field-free background. And that's what I'm going to argue is sort of an important thing. So this is what I'm talking about, the difference between magnetic flux concentrations in a volume filling background field versus isolated magnetic flux tubes. So isolated magnetic flux tubes are preconceived. You just build yourself a little magnetic cylinder. You stick it in a field-free box. So therefore, it has a flux surface which encases that magnetic structure through which flow cannot go. So it's like a hose pipe. Whereas if I have a magnetic flux concentration, as you saw, there are field lines which can thread from the background field into the structure and out of the thing. And so flow can flow along those field lines and can flow in and out of the structure. And this could actually be a very nice thing for circumventing some of the problems that have come up in people's cartoon-like description of these hose pipes. So for example, in a stratified background, if I take this hose pipe flux tube and lift it up, it has to expand, right? Because it's rising in a density stratification. And if you do the density stratification between the base of the convection zone and the surface, it has to expand by an enormous thing. So some active regions should be huge. So people try to circumvent that by saying, well, it's arched, and if you can have flow of mass down the legs of this arch, you could circumvent this. But that's kind of complicated. And if you have flux concentrations in a background field, you don't actually have that complication. You don't have to worry about that. So even just thinking simply, it's possible that thinking of things as concentrations rather than isolated flux tubes, we may be better off. And that's kind of where I'm going with this thing, that the dynamics may be substantially different. Okay, so back to this idea of the hemispheric helicity rules. Where does all this come from? Well, what's all this got to do with anything? So here's a very, very simple model of a first go at that. So this is very similar to previous models in the sense that, well, these are just 2-dimensional. So the dimensions I'm using right now, well, it's 2.5 dimensions, right? So the dimensions I'm actually simulating are X and Y, and then it has a Z dimension, but it's independent of that dimension. So this is 2.5 dimensional. But we put a tube along that Z direction, and it can have a twist, which makes you think, well, it's independent of that direction, but it has a twist in that direction. So I can have a twisted tube. And people have done these type of simulations before. The difference is in the calculations we're doing here is we say, well, okay, let's try and make it that, but in a volume filling field and see if there's any difference. So you put a background field of whatever nature you want, a horizontal background field in this case, because we were thinking about mimicking the poloidal field. So, the tube is kind of like the toroidal element, right? So we put a poloidal horizontal background field in this thing, and that's what we want to examine, right? So the interesting thing is like, well, okay, what are the strengths of these things? What's the form of the field? Kind of had this basic idea that maybe the poloidal field, going back to sort of all kinds of other things to do with tachoclines and stuff like that, maybe the poloidal field is a little more confined deeper down. There's turbulent pumping from the convection zone, which may evacuate large-scale mean fields from the convection zone. So maybe the field is stronger deeper down and weaker further up. So that is the nature of the field we're going to put in here, something which is exponentially drops off with height, strongest at the bottom, dropping off as you go up, right? And we insert a tube into that. So as you can see, very, very simple little calculations. Oh, here's the initial conditions. I don't think you care too much about this, except that just to note that, we have total pressure equilibrium to start with, so therefore we have a density deficit. So this thing is not an instability calculation, it's just naturally buoyant from the start, right? And you can look at the twist components, and the axial component is what's driving most of the magnetic buoyancy, but it is twisted, even though it's independent of the Z direction. What happens if you do this, but you vary the strength of the background field? So this is one of those things you can think, well, if I put a background field in this thing, what is it actually going to do? And immediately you think, if I have a tube rising through a background field, maybe the background field is going to wrap around it. Maybe it's going to hold it back a little bit. So it's going to make it less easy for it to rise. That's what I guessed before we actually did these things. Wasn't quite sure how it was going to work, but here is it working. So these go by super fast, but pretty quick. So over on the left here, all you're looking at is the axial field here, so you don't see the horizontal field. And on the one on the left, there is no horizontal field anyway, so you wouldn't see it even if you could see it. So this is just the standard buoyant rise. And as you can see, maybe I should slow it down, but what happens is buoyancy kicks it off, and then it gets these little vortices behind it, and the vortices advectively drive this up, and you get this funny mushroom sort of like shape as it rises. If I put in a background field, which is 10% of the strength of the axial strength of the tube, then here it goes. This is it. It still goes up. It's going a little slower, as you can see here, but it's still going up. If I put in a background field of 20%, all hell breaks loose. It can't rise. So first conclusion is, well, 20%, and that's not super strong, right? It's a fraction of the axial field strength. So it's quite surprising that I can completely defeat the magnetic buoyancy rise of this tube with a weak background field. Thing number one, but not entirely unexpected. Here's some cuter plots of those things. The thing you can ask yourself is it just tension that's doing this thing? Once again, you can see here's this one nice and cutely rising. Here you can see its little trailing vortices, which wrap some of the flux into the vortices. What's happening here? Well, you can see here the little red bits here means that there's some flux drainage down these field lines. So this thing is losing some flux, which is a bad thing for its buoyancy, right? And also, if you look at the formation of these vortices, the fact that it's pulling up this field, these white lines are the poloidal field lines, the horizontal field lines. So the red is the axial field, and the white lines are the contours of the horizontal field. So you can see that the vortices here are getting somewhat destroyed by the background field. So there's actually multiple effects here if you ask, why does a background field kill this thing? But you can see at the last one where it's 20%, doesn't go anywhere. And like I said, there's multiple effects. Yes, the tension, the trying to lift up and stretch a field over the top of you as you rise, that's one effect. But there's also the drainage of the axial flux, and there's also the destruction of these trailing vortices. So that's why this thing gets quenched quite dramatically. So it doesn't take much to quench it, about 16% of the actual thing in this case. That's not super surprising. Here's the really surprising thing. So if I just reverse the background field, what would you think would happen? Probably the same thing, right? Well, that's what I thought, but no, actually, it doesn't. There's an asymmetry because the twist is handed. So there's actually an asymmetry between, if I keep the same twist and reverse the background field, I actually get different things happening. And the thing that you find is, so here is a background field in the negative direction of 2%, and it's rising. Here's a background field of negative 6%, and it's not rising. But I don't know whether you remember, maybe it's on the next slide. Yeah, here we go. If I have a background field of plus 10%, everything rose fine. Here I have a background field of minus only 6%, and it's quenched. It doesn't rise. So there's an asymmetry here between, and here I should state up front, I can flip the background field and keep the same twist, or I can keep the same background field and flip the twist. Exactly the same thing's going to happen, right? It's actually just taking this calculation and looking at it from the other side. So I can do that. So I don't have to flip the background field. I can keep the same background field and flip the twist. So you can think of this as a way of selecting twist that preferentially rises, which of course is what the solar hemispheric helicity rule is all about. It's preferentially emerging signs of twist. They call it helicity, but it's actually twist, right? So here it is. And you can quantify this a little bit more definitely by actually measuring the rate of rise of this sort of stuff, but trust me, it happens. There's a simple explanation for this, is that it's a relationship between the direction of the background field and the direction of the twist. And the relationship of those two things can enhance or decrease. What's the opposite of enhance? Decrease, reduce the tension forces within the tube. Now, like I said, tension is normally an important part of tube dynamics because why do I need tension? It's because it's a force that acts inwards towards the center of the tube, which tries to keep it coherent. But here, if I add a background field, well, if the twist goes this way around the tube, the background field opposes at the top, it reduces the tension at the top and enhances the tension at the bottom. This means there's a net in the tube, there's a net upwards tension force, and the net upwards tension force aids buoyancy in its rise. Now, if the twist is the other way, or if the background field is the other way around, here I did it with background field, I guess. I kept the same twist, the green arrows, and the background field just reversed. Well, now the tension is enhanced at the top of the tube and decreased at the bottom of the tube. This creates a net tension force in the tube downwards, which opposes buoyancy. So it's a simple little effect, really. If I have a varying magnetic field across the tube, this is always going to be the case. I get asymmetry across the tube. And you can actually measure this in the calculations and see this is true, but yeah, believe me, it's a short talk. You have to believe me on some things. So this is a selection mechanism. I can think of it as, for a fixed twist, there's a preferential rise for a specific background field direction, or possibly better in the solar context, for a fixed background field direction, I get preferential rise of a particular twist. So it sounds related to the solar hemispheric helicity rules. Does it actually work? And the answer is yes. If I try and put this in, does it give the right-handedness for the solar hemispheric helicity rules? This is where you have to get your right-hand rules out and your thumb out and sort of check. And the simple answer is yes, but let's talk you through it. Imagine this is the sun. Imagine I have one, colloidal, my dipolar field is acting in one particular direction. I have differential rotation, which is shearing out that colloidal field to create toroidal field. Is that me or somebody else? So the red arrows are the colloidal component. The blue arrows with shear are the here's my my north to south. by the background field. So I want the twist going. Look at the handedness of that. Is it right-handed? No, it's left-handed, right? So this says that left-handed twist would be preferred to rise in the northern hemisphere. Now, if you go to the southern hemisphere, the poloidal field's still going the same way. The toroidal field is now going the other way. It's facing east, going east to west. The twist, which is enhanced, is still the same direction because the poloidal field is still going the same direction. So I still need twist going this way. And then you have to ask yourself, is that right-handed or left-handed? Now it's right-handed. So this is positive. So this fits the solar hemispheric helicity rules. And then obviously, there's a second half of the cycle where everything flips, right? So if I flip the direction of the poloidal field, what happens? Well, then I drag out by differential rotation these blue arrows. These become the toroidal field. And if I play the game again, because both the poloidal and the toroidal direction have flipped, then I'm going to get the same signs preferred. So I'm going to get negative helicity preferred in the northern hemisphere and positive helicity preferred in the southern hemisphere again, right? So cool. It works. There's lots more details of this, which in the interest of time, I'm not going to go into. The thing is that there is, for a particular value of the twist Q and a particular values of the background field, you can flip the background field or you can flip the twist. So that's like going left to right, flipping the background field, or going top to bottom is flipping the sign of the twist. And clearly these are to be diagonally symmetric because those two things, if I flip both the twist and the field, you get the same thing. But the point is here, you can look at, essentially what you're looking at here is green is go and red is don't rise. So there's an asymmetry either left and right or up and down, whichever way you want to look, between things that rise. And if there's an asymmetry between things that rise, that means there's a region in these parameter space between those two limits, or between the modulus of those two limits, where one rises and the other one doesn't. And that's the selection rule, right? And you can check this out for all kinds of parameters. And this is the bit I'm going to have to skip. You can actually make a really nice little mathematical model of this, because all you're really doing is saying, when does the rise stop? The rise stop when the internal tension of the tube, which I said is differential, the internal buoyancy of the tube, and the tension induced in the background field by rising all balance. And you can just write these down as functions of the parameters, which is essentially HB, which is the scale height of the field, which tells you how differential it is across the tube, the radius of the tube, and the background field strength BS. These are the real main parameters, and the twist strength Q. And if you do this, then you realize that the buoyancy is a quadratic term and the tension is a linear term in Q. Well, or BS, depending on which way you want to look at it, or in Q. And so if you write a quadratic here, then essentially the components of this, you've got a nice quadratic bit, which is the buoyancy, and you have this red line is the linear bit, which is associated with the tension. So if the tension is strong enough, I can bias this quadratic buoyancy part such that I get the green is the total of all these things, such that I get an asymmetric quadratic. And that's what gives you this selective rise regime of these bits. And you can check out the how this depends on parameters, all this stuff from this nice little simple mathematical model. I'm not going to talk about that too much because I don't have much time. What I do want to talk about, oh yeah, sorry. Before we go there, so there is a selection. So the question is, the solar hemispheric helicity rules is a statistical rule, right? It's something where 60% to 70% of the time this happens. Now we have a really good explanation for why that might be, because if you're outside this little selective regime, then you're either both held down, both tubes of both signs are held down, or both tubes of both signs are allowed to rise. There's only a region of parameter space, which is a region of twist strengths or background magnetic field strengths, where one rises and one doesn't. So if you do sort of like Monte Carlo type simulations where you randomly assign tubes with different twists and different spacings and all this sort of stuff, you can do these fun little simulations like this. Then you can reproduce a solar hemispheric helicity rule from the emergent twists at the top. What sign of twist gets close to the top. You can actually measure the twist in a layer near to the top of the little rising box of these tubes and see which one wins. And you get this nice thing. Whoops. Shoot. And you get this nice little fake solar hemispheric helicity rule, which depends on, I mean, if I just assign a background field strength, which is like saying where we are in the solar cycle, because, you know, the poloidal field ramps up, you know, in the cycle and ramps down again. So this sort of says where we are in the solar cycle, and then just assign a bunch of, you know, randomly assigned twists, which the simulation said that it's probably a distribution of twists. So we randomly assign twists. Then we can make a fake, you know, how much, you know, what sign of twist emerges preferentially at the top. And you can see as I ramp up the background field a little bit, but not too much, then this is a northern hemisphere calculation. Then I gradually get more and more negative helicity rising compared to positive helicity, which is the solar hemispheric way, right? This in a lot of ways is not at all surprising. You know, once you know that there is a selection mechanism that operates at some, if you randomly assign them, it's going to have a bias according to that selection mechanism, right? But it's nice that you can reproduce it. And the interesting thing is, when you do this, you still every now and again, you randomly assign a lot of twist to a tube of both signs or whatever, and they can both rise. So you do get violations to the rules. So you start getting some good feeling for why you have violations to these rules. So this little explanation explains a lot of what you see in the solar hemispheric helicity rules. Some other details. I mean, one of the things I've noticed in the calculations is potentially there's a bit at the end of the cycle where the hemispheric helicity rule is flipped. It's not negative in the northern hemisphere, it's positive in the northern hemisphere for a little bit as you change between cycles. And our model, that would be easily explained by just having the toroidal and poloidal field flip slightly out of phase. If that happened, we would see exactly that. So there's lots of nice little details here that can be explained. So immediate conclusions is that, you know, this very simple model has a remarkable agreement with many of the details of the solar hemispheric helicity rules. Okay, questions you should ask. That was 2.5D simple little calculations. Does this mechanism work in 3 dimensions? Well, here's a lot of work shown in one slide. Yes, it does. All you're seeing here is this is a 3-dimensional tube trying to rise within a positive 5% background field. Then if I flip the background field to negative 5%, you know, here it rises nice, here it doesn't rise at all, right? Uh-oh, we're off again. I got a phone in this pocket. Is it me? Couldn't possibly be me. What are you talking about? Thanks for pointing that out. Sorry about that. Okay. Bigger question should ask, oh, this was such a simple little calculation, right? I mean, flux tubes actually have to rise through a huge turbulent convection zone, right? Is it going to work in that case? Also, I arbitrarily imposed a nice exponentially decaying magnetic field as a background because I thought magnetic pumping and stuff like that might happen. Is that the right background field to impose? We can do another calculation which kills these 2 birds with 1 stone. Sorry, that sounds a little brutal these days. Maybe I should have a better phrase, but we can do both of these things at once. So I can do the same simulations essentially, but with overshooting convection, where magnetic pumping, you know, put in some sort of initial seed magnetic, you know, large-scale magnetic field and have magnetic pumping actually form a field, and then try the same game again. And we did that. And I don't have an awful lot of time, so I guess I'm going to have to go fairly quickly. So here is overshooting convection. If I talk slowly enough, I think it's going to start. Yeah, there it is. So it's 2-dimensional, or 2.5-dimensional still. The upper layer here is convecting. The lower layer here is not convecting. So here you can see nice overshoot. It's 2-dimensional, so it's not dramatically turbulent, but you got some turbulent overshooting here. Now, if I put a magnetic field in that, oh, now can I stop it and move on to the next one? Whoa, no, went too far. Oh no, I think I have to do this here because I wanted to stop. Yeah, oh, stop. Oh, I can never quite get it to stop at the beginning. So all I'm doing here, and you guys have seen simulations that Steve and I have done on this stuff years ago in 3 dimensions. But if you put a layer of magnetic field in that overshooting convection like that, then it gets pumped. That's not me.
No.
Or maybe it is. It's got something turned on.
Somebody's got their laptop on, their microphone, that's what you're hearing.
I'll keep going. Yeah, so if you put magnetic field in these overshooting convection simulations, then it all gets churned up. And over the long time, there's a mean field gamma effect, which is a mean field way of describing this actual effect you're seeing in actual turbulent convection, pumps the magnetic field into the, to the base of the overshoot zone. And for the sake of time, I'm going to accelerate this rapidly up to here, which never accelerates quite as rapidly as you want it to do. But here it goes. Come on. The evil little spinny thing. Yay, there it is. So after a bunch of time, yeah, it evacuates the magnetic field from the convection zone and the overshoot zone and puts this strong layer of magnetic field below here. This is the average magnetic field shown just to prove to you, early on it's a mess and it's all getting moved around, but after a long amount of time, you get this nice little profile of pumped magnetic field. This is magnetic pumping in action. So now I have that situation. Now I have a convective simulation. I have a self-consistent background field. So now I can insert tubes in this one. And so I can put them anywhere on this upslope here. And that's like putting them at different strengths of the background field. So I can play that game. First of all, I have to figure out, without a background field, how strong of a tube do I need to go through convection? So I can figure that out. And then I can stick it in. And here it is. OK. So here's those calculations. Over here, you're looking at the horizontal, left to right directed magnetic field. Here, you're looking at the axial into the paper magnetic field. And this one has a positively twisted tube in this case, in this sense. So this one you would expect by my just because of the way this is oriented, we would expect this one to rise, right? It's strongest at the bottom. And so here you can see there's full-on convection going on in here. There's this pumped magnetic field. I insert this tube in the pumped magnetic field. You can see it over here at the beginning of this thing. There it is. It's in there. It merrily rises. Okay. Repeat exactly the same calculation with negatively twisted flux tube. Here it is. You can see it starts over here the same way. Here it is over here. Let it go. This one goes nowhere. Gets destroyed. So end result. There's lots more details to this, of course, and you can do it for, that was one realization. Maybe I put the tube in exactly the wrong place and I needed to move it somewhere so it wasn't below a downflow. So you have to do lots of these simulations in a sort of Monte Carlo type manner to convince yourself that this is a real effect. So yeah, you can do lots of realizations and convince yourself that is the truth. The negative ones never rise. Positive ones rise. Sometimes they do get bashed around by downflows and get destroyed or whatever, but it's a pretty stark contrast between the positively and negatively twisted tubes. You can do all kinds of, so there is a selective rise regime for these things. So it carries through. You can do I picked a particular type of overshooting layer here. You can do it for different strengths of the overshooting, etc. as well. There's all kinds of details you can fill in. But the conclusion is there's a pretty convincing selection mechanism, even in the presence of turbulent convection, that provides a bias to the rise of buoyant magnetic structures that is commensurate with the solar hemispheric helicity rules. There are other theories for the solar hemispheric helicity rule, and I actually think most of them are pretty valid. I think probably all of them have some contribution to the overall helicity budget that we actually examine at the surface. And I'll just say, the handedness in the underlying mean field dynamo, this gives you a mean field helicity, and it's of the right sign. So there may be some contribution for interacting with fields which just happen to be of the right chirality already. If you look at Joy's law, that infers a rise, but actually, if you examine Joy's law, there's not enough tilt in Joy's law to give you the twist measurements that you need. So that one's maybe not so good. The next speaker has a theory about rising into the Babcock-Leighton field. That could contribute too. There's a mean field effect examined by Dana Longhope and collaborators called the sigma effect. So you can do a thin flux tube approximation, do a mean field calculation. There's a net effect. And the idea of this one is that if the turbulence is rotationally constrained, as a tube rises through turbulence, then it gets writhed with a handedness due to the Coriolis force. And because writhe and twist have to be conserved, then it gets untwisted. If it's getting positively writhed, as it gets negatively twisted. And that would give you an effect commensurate with the solar hemispheric helicity rule. And that's a distinct possibility. And the interesting thing is that there's a big difference between what we do and that idea. All of these are acquiring twist on rise, whereas ours is, we assume that there's a spectrum of twist given initially, and then it's filtered. So actually all of this stuff can work together. So ours acts early, deep in the tachycline or in the overshoot zone. It can be a selection mechanism, and then it could go through any or all of these other mechanisms on its rise as well. So in some ways, the next things we want to do is figure out, who does what, how much is done, what are the different contributions to the total overall helicity budget. And I actually have a student working on this, a non-thin flux tube, non-mean field version of this long curve sigma effect, where you have to let tubes rise through rotating convection. Now you have to do 3D simulations, which kind of sucks because it's really expensive and takes a long time. And you have to be able to calculate rive and twist in a weird object in a box, which is not very well defined. So that's what I need your help with, Keith. But as a PhD student working on that. So that's it, right? I mean, the big takeaway I think I want to say is, it's kind of cool. We have this thing which actually matches the solar hemispheric helicity rules. But the really big takeaway is that the dynamics of magnetic concentrations are very, very different from the dynamics of isolated flux tubes. And we based a lot of our thoughts on simulations of thin isolated flux tube or even fat isolated flux tube. So strength of the magnetic field at the base of the convection zone is based on a lot of these ideas, or people's ideas of the strength at the base of the convection are based on these ideas, and they may be way, way off. So if you would take nothing away from this, take away this, the dynamics of magnetic concentrations in a volume filling field are very different from isolated flux tubes. And planetary people very seldom talk about flux tubes, so maybe you should think in terms of these things. Okay, that's it for me.
Okay, we only have time for a couple of questions, perhaps. Yes.
Nick, is it possible to show just mathematical formulation of your numerical simulations for the first part for stably stratified? Which equations you solve?
Oh yeah, these are
the initial conditions.
Yeah, these are it's all in the paper, and I can give you the paper. It's probably the easiest thing to. It's a fully compressible set of equations, so we have proper magnetic buoyancy, and it's a stable stratification. It's like an m equal 1.6.
What
theta equals 10.
Current helicity of the initial flux tube
Oh right.
is 0 or not?
No, they have an initial helicity. Yes, they have an initial current helicity. Yes. Yeah, but the question is, do they get more or less? What happens to them in their transit?
And then the current helicity is changed with time during the flux tube's rise.
Yeah, I mean, the thing we're doing is the major thing we did was say, if you have the current helicity of opposite signs, then they have different dynamics. But yes, we have the evolution of the current helicity as it rises as well, for sure. Uh-oh.
Thank you. So I had a couple of questions, please. So you were envisaging these things coming from an instability, say.
Yes.
The twist is random, but if you had rotation as part of that instability, if you looked at those in the presence of rotation, that would automatically give you a bias.
Yeah,
So they wouldn't be random to begin with.
Right. I mean, that would add another bias as well. But I mean, these are just accumulating biases, right? Which I think is okay.
Okay. Do your results depend? What are your boundary conditions on your lateral on the field? Do they depend on that?
No, it's very, I mean, we've done it with different codes and different boundary conditions. I mean, most of this stuff is happening way away from boundaries. So as long as you only examine the rise well away from the boundary, you're okay. But we've done it with outflow ones and with
on the
easy
field.
ones.
On the field.
Yeah. Well, we've done it with magnetic flux leaving the thing, and we've done it with just simple, no gradient of a horizontal magnetic field type boundary conditions. Say again?
On the side boundaries.
Oh, on the side boundary. No, it's periodic on the horizontal.
Okay, but presumably that makes a difference.
Yeah, that could be. I mean, it could be that some of these things are interfering with each other because there's a series of them. Actually, no, we did do some of we did check that. We did some much bigger boxes, and we also did some with the flash code, which you can put out flux boundary conditions on the side as well.
Okay. One more quickly. You spoke in terms of percentages of background field. Presumably you can it's all to do with, I don't know, the plasma beta gives you the buoyancy, the field strength gives you the tension. Presumably you can actually get some sort of estimate for that rather than just the percentages you're getting from your simulations.
Yeah, I think you're right. And I did think about that a little bit, and I don't remember what the conclusions were. The conclusions were that, well, we can check a bit later, but the conclusions were that you don't, from an instability, you don't know what the ratio of the initial field to the strength of the thing initially is. I mean, there's some work that Jeff Fassel and I did about, what strength you would expect it to leave the layer. So you don't really know what the ratio of the background field strength is to the toroidal strength, but you can sort of estimate it, yeah. And I think we did that. It's in the paper, but I don't remember
Yeah, so my question is, the poloidal field and toroidal fields are 90 degrees out of phase. So the polar field reverses during the maximum of the activity, and therefore your selection rule would give you opposite signs in the second half of a cycle.
Well, I mean, you can depending on the phase, you can get whatever you want out of this thing, right? Our thing is that they switch roughly in phase, but you don't know what's happening deep down. And if you look at mean field models, they actually have them flip in pretty close to in phase deep down.
So at least a large scale field, which goes from one pole to the other pole, reverses with the polar fields at solar minimum.
Yeah, that's at the surface though, right?
A solar maximum. And so if you're saying some other field is important, then you need to know exactly the sign of that field. And this description you have, I don't think is sufficient to tell you whether it will be below or above where your toroidal field is.
Well, I mean, you're talking, the problem is, I mean, I understand your point, but the problem is you're talking, we don't know exactly what the phases of the fields are at the bottom of the convection zone. That's the problem. We only know it at the surface, and there's a meridional turnover time, blah, blah, blah. So depending on which model you're using.
Field lines go from one side of the sun to the other side, from the north to the south, but they can't end in between. So at some layer, there certainly has to be toroidal field, which is orientated with the large scale field. And if you say we don't know the sign of the field where it's relevant, then your whole argument for a selection effect and this magical matching of the sign becomes unknown.
Oh, I agree that this only works if the fields are in a certain sort of phase, but I'm just saying we don't actually know what that phase is.
Okay, let's move on, and I think the next one is online. Let's try to Nick again.
Okay, can you please unshare the screen so that I can try to share my screen? So can you hear me?
Yes, we can.